Hi, this is Professor Fernandez. This is video 3 in lesson 9. The topic here is calculating f prime of x, but using limits, right? Later on in the course, we'll talk about some faster ways to calculate the derivative function. So let me just remind you of the definition for f prime of x. It looks very much like the definition for f prime of a that we talked about in video 8.2 in this series, but it's got an x, so that's really the only difference. Also, I guess there's a second difference. Instead of delta x approaching 0, we have h approaching 0. It's just a little more convenient when it comes to algebraic simplification to work with h's than delta x. But we still have the same structure. This is the difference quotient. It's the change in y values divided by the change in x values. H here is again taking the place of delta x. And then at the end, we're taking the limit as h goes to 0, and that gives us f prime of x. We're thinking here again of f prime of x in terms of a function as f of x is, and the idea is that at each x value, you have an f prime of x value, right? Like before, at each a value, we had an f prime of a value. And now by changing the letters, right? It's amazing what different letters, changing letters does to our brains. By changing letters from a to x, we're signifying that x is now a variable, right? That we can input various values for x, and then out will pop out f prime of x, the derivative. So as we plot, x and its derivative value f prime of x, and we keep plotting these points, a function might emerge. So that function would be the function f prime of x. All right, so that's just a quick little review of what f prime of x is defined as in terms of the limit, and also how we get a derivative function from what we used to do with f prime of a, which is just a number. Okay. All right, I'm going to zoom back out and try this example here from Calculus Simplified. This one says calculate f prime of x for this particular function. Okay, so same thing that we were doing before with calculating f prime of a. We are going to first set up the difference quotient. So here is the difference quotient. And then I'm just going to use the function I'm given here. So I'll do the first part. I'm just subtracting the function itself. So that's the first easy part. The second part, I'm going to substitute in x plus h everywhere I see an x. Right? So there it is, and there it is. So x plus h is going to get cubed. And then I'm going to subtract 3 times x plus h. So that comes from this term. And then divide by h. Okay, so at this point, we're going to have to simplify things a little bit, and we'll do the easier simplification first. So we'll work on this term here. So I'll keep the x plus h cubed minus, I'll distribute to 3x minus 3h, and then I'll distribute the negative sign, minus x cubed plus 3x. So negative, negative gives me my plus. Then divided by h. All right, already you see some things are canceling, so things are simplifying. So this minus 3x, this plus 3x go away. Great, so x plus h cubed minus 3h minus x cubed over h. At this point, there's really no way to avoid multiplying this out. You have two options. You could view this as x plus h squared times x plus h, and then multiply x plus h squared out. Remember, this is the quick way to multiply the square of a sum. And then you could multiply this out. That's option 1. Option 2 is you could use a reference formula, or you may already know that just like a plus b squared can be multiplied out quickly using this formula, there is a similar formula for a plus b cubed. So that formula is a cubed plus 3a squared b plus 3ab squared plus b cubed. And there's a whole Pascal's triangle aspect to this. I talk about this in the Appendix A, at the end of Appendix A in Calculus Simplified. So I won't go in there. If you're interested, you can either search the web or consult that reference. But we are going to use this formula here to make our lives a little simpler. So this is the term that is getting cubed. So I'm going to make some space for myself and employ that formula. We will move things up over here. Okay, so I'm cubing x plus h. So I'm going to get x cubed plus 3x squared h plus 3xh squared plus h cubed. And then I bring everything else along for the right. So that's minus 3h minus x cubed minus 3h minus x cubed, and then divided by h. You can tell why calculating the limit, the derivative, using the limit definition is not one of the funnest things to do. Sometimes it just takes a while. This is all the reason for looking for simpler ways, right? Which we will do in the next few videos when we talk about derivative rules. Okay, so certain things cancel. X cubed here goes away with this x cubed. That's great. Left with 3x squared h plus 3x h squared plus h cubed minus 3h, all divided by h. So at this point, we could factor out an h in the numerator. Great, everything has an h. 3x squared plus 3x h plus h squared minus 3, and then we divide by h. Okay, so now we're going to use, I'm going to say the same old caveat. I am going to cancel the h's and write equals this. Again, this is not technically true unless I say h not equal to 0, because again, this quotient is not defined at h equals 0. But all of that's okay because down here in the limit definition, right, we're finding the limit to find f prime of x, which means that we don't actually care that h, what happens at h equals 0. So long story short, at the end of the day, we are taking the limit as h goes to 0 of this entire quantity. The nice thing with using technology is I can just duplicate this, save a little time. There we go. And then we're taking this limit as h goes to 0. Everything that has an h turns into a 0. So this term and that term, they have h's, they go to 0. And I'm left with 3x squared minus 3 equals 3x squared minus 3. That is my derivative function. So I'm going to zoom out here, and then I'm going to erase all this stuff, and then give you the derivative function, and then talk a little bit very briefly about how you can understand the result. So we just figured out that f prime of x is 3x squared minus 3. Great, and we did it using the limit definition. A few things you might notice here. The original function was cubic. The derivative is quadratic. Is there a pattern? You know, if the original function was, x to the fifth, fifth order polynomial, would the derivative be a fourth order polynomial? I don't know. So I'm planting seeds in your mind to start thinking, well, is this a general pattern, or is it just, something that's true for this particular f of x? Another thing that should also kind of make sense, the function f is x cubed minus 3x. 3x is a linear function, right? The slope of y equals 3x is 3. If I graph y equals 3x, it looks something like this. And if I pick any points, right, whatever x value, and I'm looking at the value of the function, and I draw the tangent line on that point, the tangent line has the same slope as the original line because the original graph is a line. So the tangent line will have the same slope, meaning the derivative will also be 3. And there it is, showing up in the derivative of f of x. So perhaps, maybe the derivative of a difference of two functions is the difference of the two derivatives, right? That's the other seed that I'm planting in your mind, that maybe there are rules and properties that derivatives satisfy. Okay, so that is a really quick review and seed planting for what happened here with this example.